All right, so we're in section 12.4 and talking about tangent and normal vectors. We talked on Friday. We talked about velocity and acceleration, and I just want to summarize really quickly. When we have some vector valued function, we're thinking of. On Friday, we talked about the r of t being a position. We decided that r prime of t was tangent to the curve. Represented by our position vector, represented by r of t. And it points in the direction of increasing parameter. So that's this. On Friday, when we talked about projectile motion, we said that the velocity vector points in the direction of motion. If we're talking just a general vector valued function, then r prime of t points in the direction of the increasing parameter. So again, on Friday we talked about r of t being a position vector. R prime of t would be the velocity, and in general we can use our parameter our parameter can be anything, and our r of t can be any vector valued function. It doesn't have to be a position vector, and we don't have to be talking about time as a parameter. So what we're interested in using r prime, using our derivatives to write an expression for a unit tangent vector. And our unit tangent vector and our unit normal vector are going to be very useful to us moving forward. So our unit tangent vector you'll usually see it notated with a capital T. Is going to be, and this is a function of t, our unit tangent vector changes with time, is just going to be given by r prime of t divided by the length of r prime of t. And that gives us our unit tangent vector. And this is our definition where on any interval where r prime of t is not equal to 0. And if r prime of t is not equal to 0, we're saying, remember we said that meant that our curve was smooth. So we have a smooth curve on the interval where we're looking at our unit tangent vector. So let's take a look at one example of where we would use a unit tangent vector. And this we had a problem like this on the board on Friday. I don't think anybody got to it on Friday. So let's say r of t is the vector e to the minus t, 2 cosine t, and 2 sine t. We want to find a set of parametric equations for the tangent line to the graph at t0 equals 0, and we want to approximate, use this to approximate r of 0.1. So before we go on, what is this curve? What is this curve going to look like? Anybody have an idea? It's going to spiral. And remember, with vector valued functions, we don't get a surface, we just get a curve. So right, so Scott says it's like a spring, so it's like it's getting stretched out. So when the 2 cosine t and the 2 sine t in the j and the k components, that's going to give us a circular motion parallel to the yz plane, and the e to the minus t is a exponential function. So as t increases, it's going to kind of circle. It's like the spring is getting stretched out, or the string has been stretched out. And near t equals 0, it's going to the I component is going to be very small, so it's moving. It's like it's less stretched. It's like a stretched out spring. So we want to figure out the equation for a tangent line at t0 equals 0. What do we need to write an equation of the tangent line? We need the derivative. The derivative would give us what? So if we want to write parametric equations for a line, what do we need to write parametric equations for a line? Remember back to chapter 11? We need a vector, we need a parameter, we need a vector in the direction of the line, and we need a point on the line. That's what we need to write our parametric equations for a line. So our direction vector, what's going to give us our direction vector for our line? The derivative, r prime. R prime is going to point in the direction of the tangent line. So let's write an expression for r prime. R prime of t is going to give us a vector in the direction of the line. So what's going to be r prime of t? Negative 2 sine t and 2 cosine t. The length of r prime is going to be the square root of our component squared. So it's going to be e to the minus e to the minus t squared plus negative 2 sine t squared plus 2 cosine t squared. And if we work that all out, do our algebra, we end up with r prime is the square root of e to the minus 2t plus 4. R prime of 0, because we want the direction vector, the vector in the direction of our tangent line at time 0. So the length of r prime at 0 is going to be the square root of 5. And finally, our unit tangent vector at time 0 is r of 0 divided by r prime of 0. And that gives us square root of 5 over 5 times negative 1, 2. Our unit tangent vector, this is, I did r of 0 divided by the length, or sorry, r prime of 0 divided by the length of r prime at 0. So r prime at 0 is going to be negative 1 and 2. And we have no, let's see, 0, sorry, negative 1. I forgot my 0. Negative 1, 0, 2.
So
Sorry.
why is it square root of 5 over 5?
Because I'm dividing by the length of r prime.
Oh,
So
okay.
this is, so I have to do 1 over this.
Fine. Okay.
So this is my unit tangent vector at time 0. And the r prime of 0 gives me my direction vector. So r of 0 is, sorry, r prime of 0 is negative 1, 0, 2. And so our direction numbers for the line are, we don't need to worry about this. We're just looking at the direction, so we don't need to worry about this magnitude. A is negative 1, B is 0, and C is 2. And r of 0, we need a point on the line. So our position vector, r of 0, is 1, 2, 0. So our point on a line so the point on the line is the point 1, 2, 0. And now we can write our equation, our parametric equations for the line. We have our direction numbers and we have a point on the line. So our parametric equations are x equals 1 minus t, y equals 2, and z equals 2t. So those are our parametric equations for our line. Remember, our parametric equations were x equals x0 plus at, y equals y0 plus bt, and z equals z0 plus ct. Yes?
So where does the t of 0 come in your 5 over 5? And did we need to use that?
We didn't really. I just calculated our unit tangent vector. Our derivative, our r prime, gave us our direction number, but I just calculated the unit tangent just to do it. Okay?
Would that be a question now? Ever? Just like calculating the unit tangent?
We'll use a unit tangent vector in just a minute to calculate our unit normal vector.
Okay.
And we'll use the unit tangent vector when we talk about the components, the normal and the tangential components of acceleration, because we're going to break our acceleration into two components, one that's tangent to the direction and one that's normal to the direction of motion. That's when we'll use it. I just did it just to do it. All right, and then we want to approximate r of 0.1. So instead of plugging 0.1 into my function for r of t, here, I'm going to use the tangent line, the equation for the tangent line to approximate r of 0.1. So I can say that r of 0.1 is approximately, I'm going to use the tangent line, is 0.9 to 0.2. I just plugged in 0.1 for t in the equations for the tangent line and used that as an approximation for the value of the function at that point. Questions on that problem? This type of problem is one that the book likes to ask about a lot, is calculate the equations for the tangent line and then use it to approximate the function. All right, so we have a method for calculating our unit tangent vector. We want to be able to find a specific vector that's orthogonal to our unit tangent vector. So we want to be able to calculate a normal vector, a vector that's perpendicular to the direction of motion. Our unit tangent vector is tangent to the vector of motion. We want to be able to calculate a vector that's a 90-degree angle to that. So we're looking at our unit normal vector. And remember back when we talked about properties of the derivatives of vectors, and I said there would one property that would come up a little later. And we said that the derivative, that property was if r of t dot r of t equals a constant, that r dot r prime, r of t dot r prime of t equals 0. So this was our property that I said would come back and be important. So let's look at how we're going to use this. We defined t to be a unit vector. T is a unit vector by definition. So we know t dot t equals 1. Remember the dot, if you take the dot product of a vector with itself, you get the magnitude squared. So because t is a unit vector, t dot t equals 1. So t dot t is a constant. This means that t dot t prime has to equal 0 by this property. And the proof of this property is pretty easy, pretty straightforward. If you're interested, I can show it to you. It's an easy proof using the dot product. But by this property, t dot t prime is going to be 0. And because the dot product is 0, that tells us that t prime is orthogonal to t. So we normalize t prime to get our unit tangent, our unit normal vector. So our unit normal vector, and we usually write it, the unit normal vector n, capital N, and it varies with t, is t prime over the length of t prime. And we want t prime not equal to 0. We also want r of t is smooth. So our unit normal vector, we find our unit normal vector by taking t prime, the derivative of our unit tangent vector, and dividing the derivative of the unit tangent vector by the length of the unit tangent vector at a particular point. And I'm going to rewrite this. I'm going to put our functional dependence on our parameter, just so we remember that that our unit normal vector changes with time. And a couple of important points about the unit normal vector. N of t points to the concave side of the curve. Or you can think of it as it points in the direction that the object is turning. So if you think of our curve representing a motion in space, our unit normal vector points in the direction that it's turning. And that's the same as saying it points to the concave side of the curve. Because our unit, we could, depending on how we calculate our unit normal vector, it could point in either of two directions. But we want our unit normal vector to point towards the concave side of the curve. Questions on our definition? Okay. Let's look at an example of calculation. We want to find our unit normal vector at t equals 2 for r of t equals ti plus 1/2 t squared j.
So for the normal vector and stuff,
Mm-hmm.
is that only in 2 dimensions?
No, it 2 or 3 dimensions.
Okay.
It works for any vector. All right. So what's going to be r prime? R prime is going to be I plus tj. Length of r prime. Length of r prime is going to be 1 plus t squared. So our unit tangent vector is going to be 1 over 1 plus square root of 1 plus t squared times I plus tj. Now we need to find, in order to find our unit normal vector, we have to find t prime. T prime of t, so we have to take the derivative of this expression. I'm not going to go through all the steps to find the derivative here, but our derivative comes out to be minus t over 1 plus t squared to the 3 halves plus 1 over 1 plus t squared to the 3 halves j. It takes a little work and a fair amount of algebra to write r, and this should be I, to write this expression. The length of t prime. Now if we wanted the length of t prime as a function of t, you can see that this gets messy very quickly. Let's just calculate it at the point we're interested in. T prime of 2. T prime of 2 gives us negative 2 over 5 to the 3 halves I plus 1 over 5 to the 3 halves j. So I'm just substituting t equals 2 in here. The length of t prime of 2 is the square root of negative 2 over 5 to the 3 halves squared plus 1 over 5 to the 3 halves squared. And when we simplify that, we get 1/5. So finally, let's see, so we have the length of t prime at 2, we have t prime at 2, so we can find our unit normal vector. Our unit normal vector at 2 is we did. Sorry, our unit normal vector at 2 is 5 times our times t prime at 2, which is, we said, was negative 2 over 5 to the 3 halves I plus 1 over 5 to the 3 halves j, which we can simplify to square root of 5 over 5 times negative 2I plus j. Questions, guys? Now, you can see if we added a component, if we added a z component, calculating these derivatives, calculating the length of these derivatives, gets very algebraically, it gets kind of complicated pretty quickly. But in the plane we have a shortcut, and I think that might be what you guys were seeing. In the plane we have a shortcut. If we have a unit tangent vector in the plane, let me make sure before I move on, is everybody good with what we did here? We just calculated t prime, and normalized our vectors. All right, so in the plane we have a shortcut. If we're looking at motion in the plane, if you have a nice problem in the plane, if we have if our unit tangent vector is some function of x of ti and y of tj, so we have two components, and we know that the length of t equals 1 because it's a unit tangent vector. So the square root of x of t squared plus y of t squared has to equal 1. Our magnitude is 1. We defined our unit tangent vector as magnitude 1. And we know that n, our unit normal vector, is orthogonal to t. So if we think of the vectors, if we think of the slope of the line that is in the direction of the vectors, if they're orthogonal in the plane, what relationship do the slopes have to have? How are perpendicular lines, slopes of perpendicular lines related? Negative reciprocal. So if we think of the slope of the, and I'm using slope in parentheses, if we think of the slope of the unit tangent vector and the slope of the unit normal vector, the slopes of those two have to be negative reciprocals. So n is either, we just switch the x and y and change the sign on 1. So n is either y of t I minus x of t j, or minus y of t I plus x of t j. If we think of the components, y over x being the slope, in order to get negative reciprocal, we just switch the y and the x and change the sign. So we can just switch the y and the x and change the sign on one or the other. And we pick the one that points in the direction to the concave side of the curve. So in the plane, you have this little shortcut that you can just switch the x and the y and change the sign on 1 to get your unit normal vector. For x, y, and z in 3 dimensions, that doesn't work. But if you have a nice problem that's just in a plane, this is how you would find your unit normal vector much more easily. And because t is a unit vector, the square root of x squared plus y squared equals 1. These n has the same components. So n will also equal 1 here. So in the plane, if we have our unit tangent vector to find our unit normal vector, we need to switch the x and the y components and change the sign on 1. And if we look back to our example that we just did, if we look at our unit tangent vector at the point 2, if we switch the x's and the y's and change the sign on 1, we would end up with the same thing. Questions? Okay. Let's look at our homework. Page 863. There you go.